Hello, George Romanic here. Today we are going to study thermal conductivity of an ideal gas, and we will derive a closed-form solution for coefficient of thermal conductivity. I suggest you check my previous video on coefficient of viscosity and viscosity of ideal gases, because today's video pretty much follows the same concept of that video. However, here we are not talking about transfer of momentum when we have collisions between atoms of ideal gas that was responsible for viscosity. Here we are going to talk about transfer of mean kinetic energy when atoms collide, and that results in thermal conductivity because temperature is a measure of mean kinetic energy of a gas. I suggest you check my video on temperature of a gas to properly understand definition of temperature from the point of view of kinetic theory of gases. This video once more demonstrates that it is very important to study physics at a more fundamental level than the field you are interested in. You see, if you are interested in thermodynamics and fluid dynamics, then coefficient of thermal conductivity is just a coefficient. It's a number we plug in some equation and we calculate something. But you see that coefficient of thermal conductivity can actually be derived in a form of closed-form solution, as we will do it today, and it can be derived using the concepts of kinetic theory of gases, and we will see that it's maybe not coefficient, rather it depends on average speed of atoms in a gas. It depends on mean free path of atoms in a gas, and so on. We could go even further, and maybe we will one day on this channel, and then we have to go into quantum physics and other more fundamental levels of physics to explain this coefficient and other processes in a gas at even more fundamental level. For now, we are satisfied with kinetic theory of gases, and we are satisfied how that theory describes thermal properties of an ideal gas. Before we start with derivation, I would like to ask you to share this video with several people, friends and family, enemies perhaps. That will help growing this channel. Now let's start. We are going to look into a condition where we have an ideal gas, like so. It's a bunch of small spheres, particles, and temperature of this gas will depend on some axis, let's say z height, and this is my axis z. From my video on the temperature of a gas, we know that temperature is proportional to the average kinetic energy of atoms in a gas. That means temperature is proportional to this average kinetic energy of atoms in a gas, where m is mass and v squared, or rather v is speed of these atoms squared. But because we assume here this is all same gas, mass is a constant, this is not radioactive gas, so it is not changing, so this becomes simply 1 over 2m average of v squared, and this is the infamous mean square speed. I have video on this quantity, and I told you this quantity is particularly important for temperature, and you can see here that's the case. Now this is in terms of proportionality. Again, in my video on the temperature of a gas, we saw that constant of proportionality that people introduced to relate these two quantities is 2 over 3 divided by k, where k is Boltzmann constant, and then we have 1 over 2 m mean squared speed. And this is temperature of the gas, which means if temperature is changing along this axis, this is the quantity that is changing, because k and m are constants. Really, it's mean square speed of atoms that is changing. So if we assume, let's say, that this northern part is hotter than the southern part of the gas, that means this part over here is jiggling more, has higher mean square speed than the bottom of the gas. So in terms of, let's say, arrows, this part of the gas would have longer arrows. It's chaotic motion. Gas is moving in any, particles are moving in any given direction. But on average, we have long arrows here. And here we have shorter arrows than the one above. That would mean that temperature is increasing with height. Now already from this figure we can see that these atoms are moving in any given direction. So I will define a quantity called small n to be number of atoms per unit volume. And we know from my previous videos we basically define this as capital N divided by V, where capital N is total number of atoms in this volume, whatever that volume is. And we like to always work with quantities that are given per unit volume, per unit time, unit surface, and so on. And that's how you get number of atoms per unit volume. Divide total number of atoms with total volume. Now, because this motion is chaotic, 1/3 of atoms on average will move along z-axis. That means 1/3 of this n will go up, down. Now 1/3 of this n will go along the x-axis. So this is z-axis, this is x-axis, into the page, out of the page. And 1/3 of these n atoms will move along the y direction, left, right. But in this video we are going to look into this case, and then clearly the same result applies to two other directions. Now we can clearly further see from here that 1/6 of these n atoms is going to go up, namely half of this, and 1/6 of these n atoms is going to go down along the z direction. That means if I introduce somewhere here a plane at some arbitrary height z. Now I want to be more specific and look into how many atoms will cross unit area of this plane in unit time. Because, as I just said, we like to work with quantities that are defined per unit second, unit time, unit area. So if I replicate here this unit surface on my plane z, it would look something like that perhaps. So area of this surface is 1 unit. And I'm, let's say, interested into atoms that are coming from underneath. So there will be atoms crossing this plane coming from underneath. The question, how many of them in 1 second? Well, clearly there will be some distance below the plane that the atoms must be within from the z plane to pass this plane in 1 second. So all atoms here that have velocity towards the plane will cross it in 1 second. The one that is here on another atom that is here, they might cross this plane, but not in unit time, in 1 second, let's say. So therefore you can see there is some critical, let's say, height from the plane that the atoms must be to cross this plane in unit time. And this height, coupled of course with surface, will give us this critical volume that the atoms must be in. So this critical volume is clearly this area, but that area is unit, I just said here, times this height zc. So this becomes 1 times, but this height zc is average speed of atoms times some time interval delta t, but I just said we are interested in unit time interval, so this is 1. So this ends up being average v, where average v is the mean speed of atoms. So that means that n over 6, this quantity, multiplied by v, is the number of atoms crossing this arbitrary z plane in unit time per unit area of this plane. Now I would like to go back to this figure and introduce two planes adjacent to my plane Z. And one will be, let's say, here above Z, and another one will be below Z. This plane above will be at a distance lambda. So this is at Z plus lambda. And this plane below will also be at the distance lambda, but below, so this is at Z minus lambda. Where lambda is the mean free path of atoms, namely average distance atom travels before colliding with another atom. That means that on average, atoms crossing this Z plane from below will have their last collision at this plane Z minus lambda. Similarly, the atoms that are crossing this Z plane from above will have their last collision at this height Z plus lambda. And because temperature is changing with height, the atoms that are coming from above will bring higher value of this average kinetic energy than the atoms crossing this plane from underneath. Which means gas from above will basically heat up gas from underneath, and that's conduction of heat that we are talking about in this video. Why would that be the case? Well, these atoms that have higher kinetic energy that are coming down are colliding later with these slow moving atoms, and in these collisions they give some of their kinetic energy to these atoms, so these slow down, these speed up, which means these lose energy, these gain energy, and eventually we get temperature equilibrium where gas is well mixed and at the same temperature throughout. Very well. If we combine number of atoms crossing plane in unit time and per unit area of that plane with the average kinetic energy of these atoms, then if I multiply these two quantities, I will have average kinetic energy of atoms crossing the plane from either above or below. In other words, n over 6 times v, this quantity, and then times 1 over 2 m mean square speed. But let's say mean square speed evaluated at Z plus lambda. That will be average kinetic energy of atoms coming from above in unit time and per unit area. Similarly, n over 6 times average v times 1 over 2 m, and then mean square speed evaluated at Z minus lambda. This evaluation line should really be outside of this bracket here, so keep that in mind, is average kinetic energy of atoms coming from below and then per unit time and per unit area. Which means we can define the difference between this quantity and that quantity, and that difference is clearly net flux of these atoms carrying this mean kinetic energy. So I can define a quantity, let's call it JQ, that will be this amount of kinetic energy being transferred upwards minus the amount of kinetic energy per unit time and unit area transferred downwards, and therefore this JQ, I can call it net heat flux, also known as heat current. Okay, so this quantity therefore becomes n over 6 times V times 1 over 2 m mean square speed evaluated at Z minus lambda minus this over here, n over 6 average V times 1 over 2 m mean square speed evaluated at z plus lambda. But now I will go back to this expression over here, and you can see that the average kinetic energy can be written as 3tk divided by 2, and that's what I will now substitute here, and I will cancel now 3 and 6 and so on. So upon substitution, one will get that JQ is equal N average V times Boltzmann constant divided by 4 and times temperature at height z minus lambda minus temperature at height z plus lambda, where I assume that z is height, but it can be any axis really. We find these quantities using Taylor series expansion with respect to the reference plane z, and we will keep only the first two terms and neglect higher order terms. So JQ becomes N average V times K divided by 4. Now this quantity over here, that is temperature at height Z minus delta T delta Z, namely rate of change of temperature along Z, and times the increment, and the increment is lambda. And then we have minus, now I decompose this quantity using Taylor series, so that will be temperature at level Z plus, but because of this minus, it's going to be minus delta T delta Z times the distance, and that is lambda. And plus higher order terms, but as I said, I will neglect these. So you can see that this and this quantity nicely cancels, and we get here that JQ is equal, I will have when I sum up these two, I will have a coefficient of 2 that will cancel with this 4. So I should have N times V times lambda times K divided by 2 delta T delta Z. And this quantity, ladies and gentlemen, boys and girls, is the net heat flux, and you can see that net heat flux depends on the temperature gradient, and there should be minus over here because of these two minuses, and the proportionality constant between the net heat flux and the temperature gradient is this factor over here, and that factor is known as the coefficient of thermal conductivity. So this is coefficient of thermal conductivity. So one more time on the next page, JQ was equal negative K delta T delta Z, where this K is equal N average V times lambda times K divided by 2. And units of this coefficient of thermal conductivity, we often use capital K, is watts per meter and per Kelvin. This equation is a very famous equation. It is often introduced in elementary courses in physics, atmospheric sciences, but the physical meaning of the coefficient of thermal conductivity is not readily available in literature, at least in these introductory courses. But now, from this video, you see how kinetic theory of gases gives us the value of K beyond just being some coefficient of proportionality between these two quantities, but gives us explanation in terms of fundamental quantities of our gas. Number of atoms per unit volume, their average speed, mean distance they traveled between collisions, and a universal constant, namely Boltzmann constant. And number 2. If you don't know anything about number 2, go and watch beauty bloggers. Why are you watching this video? You can also see that this negative sign tells us that the flux and the gradient are acting in the opposite directions. Namely, look, when delta t, delta z is positive, because of this negative sign, means that JQ will be negative, and that means if temperature is increasing along the z height, there will be net transport of heat in the negative z direction. This negative sign also ensures, in other words, that this K is always a positive quantity. Here is a table that shows the values of the coefficient of thermal conductivity for some typical gases found in our atmosphere, including radon as an extra gas. And you will remember from my previous videos, we covered all these other characteristic quantities in terms of kinetic theory of gases, and the only one that is left, at least for now, is the coefficient of thermal conductivity. And you can see the values for these typical gases. For example, carbon dioxide, thermal conductivity coefficient is 0.0053. Now I would like to discuss further this finding. I would also like to tell you that this coefficient of 1 over 2 is uncertain, and different values of this coefficient can be obtained if one tweaks a little bit our derivation that we just conducted. To demonstrate that this coefficient can be different, I will derive this same coefficient of thermal conductivity, but using different arguments. For example, in my video on temperature, you will remember that we defined quantity U to be mean internal energy of the gas. Now, if gas is monoatomic, we said this energy is only translational energy, namely kinetic energy. But if we have more complicated atoms, then this internal energy also consists of vibrational energy as well as rotational energy of these molecules and atoms. In that case, if we account for all these and we say that this mean internal energy of the gas depends on temperature, higher temperature, higher jiggling, higher vibration, higher rotation, higher translation. So higher temperature, higher mean internal energy. But we just said that temperature is changing with height in previous page. So you see, without now replotting all these figures, I could say that JQ is equal 1 over 6 N average V. This stays the same because that's the number of atoms crossing our Z plane per unit area of that plane and per unit time, times this quantity now, U, evaluated at Z minus lambda, minus U, mean internal energy of the gas, evaluated at Z plus lambda. Or this is further equal 1 over 6 N average V. Again, I use Taylor series expansion for these quantities, so this will be U at Z minus delta U delta Z times lambda minus U at Z minus delta U delta Z lambda. And once again, this and this cancels. And you will now see that JQ becomes 1 over 3 N V delta U delta Z times lambda and everything with negative sign. But that means that JQ is further equal negative 1 over 3 N average V times lambda. Look, delta U delta Z, but U depends on T, so we use chain rule to say that delta U delta Z is really delta U delta T delta Z. And this is another way a person can derive our net heat flux, where this quantity over here, we often denote it with small letter c, is known as the specific heat per molecule. And this over here, as before, is our K. coefficient of thermal conductivity, which means JQ is equal in this way negative K times C delta T delta Z, but quite often, very often, books combine these and they call K combination of these, and then you would get that JQ is simply equal negative K delta T delta Z. So, I gave you here these two alternative ways. Sometimes they write it like this, sometimes they put C to be inside of the K. At any rate, that doesn't matter, that's just technicality. If we do it this way, then you will see that coefficient of thermal conductivity is negative 1 over 3 n average V times C times lambda. And you will see that this coefficient has different value of this parameter compared to this coefficient over here. Here we had 1 over 2, here we had 1 over 3. And that's because technicalities of this derivation are different from the derivation I had in the previous page. You will also observe in either of these definitions that coefficient of thermal conductivity is independent of the pressure of the gas. And I will not explain here why, because it's the same reason for which coefficient of viscosity is independent of the pressure of the gas. So you can check my video on the coefficient of viscosity and you will see the argument why these coefficients are independent of the pressure. Now let us look a little bit closer at these two definitions of this beautiful coefficient of thermal conductivity, because they both represent the same quantity derived using different means. I can equate them. And if I equate these, I will get 1 over 2 average V lambda K, that's this guy, equals this guy over here, n V C lambda. Notice that lambda and lambda cancels. V and V cancels. Oh, I forgot n over here. N and n cancels. And I will get here that C is equal 3 over 2K. So a very nice relationship between Boltzmann constant and specific heat per molecule. In my previous video on viscosity of the gas, we saw that coefficient of viscosity 1 over 3 is equal 1 over 3n average V times mass of atoms times lambda. But look, here we have K that is equal 1 over 3n average V C lambda. So they are very similar. And indeed, if we make a division K over eta, we get that that is equal C over M. So this is a nice relationship between these two coefficients. Now I would also like to say that kinetic theory of gases gives better prediction for coefficient of viscosity than coefficient of thermal conductivity. If we, for example, how should I say this? If I multiply this quantity by M and divide by C, I will get K divided by eta times N divided by C, and that will be 1. So we see that if we know these coefficients and we multiply by M divided by C, we should get 1, according to theory. But experiments really show that instead of 1, this quantity is more somewhere between 1.3 to 2.3, 2.5, something like that. Now you might be disappointed, but you shouldn't, because in many cases, as you can see here, these quantities are several orders of magnitude below our everyday distances, so we are not messing up orders of magnitude in these cases, it's just a coefficient. And keeping in mind how simplistic these arguments are within the context of kinetic theory of gases, it's really surprisingly good result. We are not invoking any quantum dynamical effects, we are not invoking any electrical interactions between atoms and molecules that always exist, and still without taking that into account, we get surprisingly good result. And I'll discuss soon what are some of the reasons for this discrepancy that are within the context of kinetic theory of gases, but we didn't consider them here. Before I do that, I also want to tell you that in some books, these quantities are given as molar specific heat. So C would be multiplied with that ugly number called Avogadro number, and then this is called molar specific heat, and mass would be multiplied with Na to give molar mass, where Na is Avogadro number, 6.02214 times 10 to power 23 anything per mole. And I talked more about Avogadro number in my video on equation of state, so you can go and check that out. I would like to now discuss some of the reasons for this discrepancy, and these reasons being within the context of kinetic theory of gases. You will remember that Maxwell-Boltzmann distribution is skewed and looks something like that, is positively skewed to the right, where here is probability density function of velocity, and here are different velocities. You see, everywhere here in this entire theory we are only using mean speed. Now don't be beckon and think that this is mean speed, because distribution is skewed, mean speed is somewhere here. Check my video on the mean speed. This would be mode speed, this would be median speed, this would be root mean square speed. Now I gave you overview of the entire table that it took us few months to cross. But you see, it's not that all molecules have mean speed. Some are moving slow, some are moving fast, and the distribution is skewed to the right. That means that the faster atoms, if we have a unit area that the atoms are crossing from underneath or from above, faster atoms will cross this area more often than these slow atoms. And that is not accounted in this theory that we just developed. Now, this plays important role in the case of thermal conductivity, and this doesn't play important role for viscosity, because in terms of viscosity, we are interested in the mean component of momentum parallel to this plane. So you can see if K increases, and that's because more fast atoms are crossing this plane than slow atoms, eta is pretty much the same. So if this increases, this stays the same. That means that this ratio K over eta will increase. And you can see that justifies some of this increase that experimental physicists found. For example, if we go back to our table, actual value of the coefficient of thermal conductivity for carbon dioxide at 23 degrees Celsius is 0.016454, and that is approximately 2.5 times the value that we calculated using kinetic theory of gases. So you can see that we can justify quite well the discrepancy using these qualitative arguments. Of course, these qualitative arguments could be quantitatively described, but that's not going to happen in this video. This video described thermal conductivity of ideal gases using the concept of kinetic theory of gases. What we saw at the end of the day is that if we have, let's say, two layers in an ideal gas, atoms in this top layer are jiggling faster than the atoms in the bottom layer. There will be exchange of jiggling, and by jiggling we mean mean kinetic energy of atoms in that layer, namely the atoms that on average have more kinetic energy will give some of it to the atoms in the colder layer, and then the colder layer will heat up and the warmer layer will cool down, and eventually after some time we will reach thermal equilibrium. All these can be explained, as we saw today, using the concepts of kinetic theory of gases, and never forget, entire kinetic theory of gases is based on Newton's laws. So once more we have contributions of this great man, Sir Isaac Newton, into the field that perhaps he wasn't even aware of. Newton's laws are the backbone of kinetic theory of gases. All these collisions are described using Newtonian mechanics. Therefore, it is very, very important to study fundamental physics, mechanics, thermodynamics, kinetic theory of gases that we did in today's video. Before the very last closing remark, I would like to ask you to share this video with several enemies, friends, and family, so we keep this channel growing. Until next video, goodbye.